Sir, yes. Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Abhinav. Okay. Good evening to one and all present today virtually in the eighth webinar of Assam Artificial Intelligence Initiative. I welcome you all on behalf of Team I to this program. I is an initiative to promote AI in the Assam Northeast region and to build an academic network for students, researchers, and AI enthusiasts to exchange knowledge. Now, we all know that today we are living in the era of big data. But have you ever wondered how Google data centers work? Or what are the physical infrastructures required to enable the day-to-day Google services that we use? How are Google engineers trying to minimize carbon emission in their data centers? Well, to answer all these questions and more, we are lucky to have with us Dr. Saurav Talukdar from Google USA, who will be giving a talk titled Introduction to Data Centers and Carbon-Aware Computing. Dr. Saurav is a control system engineer at Google USA, where he is working towards improving the efficiency of Google data centers. Before joining Google, he did his PhD from the University of Minnesota, and he is an alumnus of IIT Bombay, where he pursued his Bachelor of Technology and Masters of Technology in Mechanical Engineering. His research interests include optimization-based control, statistical modeling of data center power utilization, and carbon-aware computing for data centers. So without any further ado, let's begin the talk. Before that, just a note for those who are watching the live stream on YouTube, you can drop your questions in the live chat and we'll be happy to forward them to Saurav sir. So with that, I would like to hand over the session to Dr. Saurav Talukdar.
Thanks, Abhigyan, for the nice and kind introduction, and also to Shishir and the whole I team for giving me this opportunity to come and interact with you all. Yeah, I think kind of quite a unique platform, I think, which I is trying to put together to bring together the people working in the field of AI and data science broadly from all over Northeast as well as in the industry together. So this is, I think, gonna be very useful if I look at it from a long-term perspective. So yeah, I think before I get more into the details of the topics that probably I'll be covering through some of the slides, I just wanted to give some background, more from maybe things probably which Abhigyan didn't cover. I grew up actually in Khanapara, neighborhood of Guwahati. So yeah, if there are some of you out there from that area, special hello and namaste. Apart from that, in Guwahati, I actually went to two schools for almost all my education. One was this till 7th, I studied in Srimanta Shankar Academy in Dispur, and then from 8th till 10th, I went to Delhi Public School, which is more towards the highway in Guwahati. After that, I moved to Kota for a couple of years, and then I was in 5 years later, and for 5 years I was in IIT Bombay for my bachelor's and master's. Apart from that, I think I think one of the favorite probably spots in Guwahati for me is actually near the Uzan Bazaar area, near the Brahmaputra shore. It's one of my favorite spots out there, which I always, whenever I visit, I like to go there. I actually regret that I have not been able to come back for almost 2 years now, actually, because of COVID. So yeah, hope to make it back soon, and then yeah, maybe I'll be able to meet some of you, and we'll hang out somewhere in Uzan Bazaar. Okay, with maybe some that kind of a background. Now maybe I'll start getting more into the area of data centers, and I think just to give one maybe connection here. As Abhigyan was telling, my background is primarily in mechanical engineering, and that should at least maybe some of you may be wondering, like, how does a mechanical engineer fit into like a technology or an internet-based company like Google? And hopefully this talk will give some perspective into that about how not just mechanical but other disciplines of engineering come together to enable, let's say, a very computer science and software engineering driven business, which typically all Google products are very, when you look at it at the user side, are also essentially software. It could be search, be it YouTube, be it maps, and so forth. But the back end of it, how do other disciplines of engineering actually come together to provide that software service to all the different users? So yeah, let's get started with this, and over the talk is, and the way I have kind of put together a slide is that I've kept it at a very high level, but there will be links for references, and like you see on the first slide here itself. So it essentially is a link to the technical paper that's still under review on this topic of carbon-aware computing that we have written. And other slides also will have this kind of links, which are kind of more detail oriented. So my slides are more high level and are at a generic level, so that the audience here is very broad and to be accessible to everybody. But there will be these kind of links in some of the slides, and those will be for details for anybody who is very interested to follow up. And feel free to reach out to me as well on LinkedIn or any other social media to actually get further clarification on any of the questions you may have, which we may not be touching or due to our time here. The slides have been shared with Shishir, so he can share the link with the audience here, so that if anybody wants to take a look at the slides later, they can also have access. Okay. So what is a data center? That's, I think, one of the first things I want to get to. But before getting to that, essentially the logos that you see in this screen, starting from search, Android, and all the way to Gmail and Google Photos, all of these services, which many of you may be using on your day-to-day basis, all of these are actually being provided to you from the data centers of Google. So whatever you want to go from place A to place B, you type in a query, and then that essentially gets answered in some data center. I think in India, if I have to give you locations, probably we have data centers in Bombay and Delhi, Gurgaon, essentially. Overall, there are I think about 100 or 134 locations all over the globe where Google data centers are present. And the way the infrastructure is designed is that it's even if one location goes bad for whatever reason, let's say there is a big catastrophic weather, hurricane, or a flood or something, because of which certain power failure happens somewhere, and so we cannot run that data center. The infrastructure is designed in a way that all your requests to see a particular YouTube video will get rerouted to some other closest data center, and your requests will be served. So just to give you an idea about what kind of, let's say, maybe there's some kind of reliability and robustness that's being built in designing this infrastructure, which is essentially a network of several data centers all over the globe. Overall, moving on, well, I'm trying to get to, let's say, what is a data center? And I'm kind of trying to simplify it here, in the sense that it's a bit more complicated than this. But I'm just trying to give the picture of data center, which, let's say, should be good enough for the purpose of our discussion today here. Overall, before may think of it like this. Let's say that all of our laptops, right? Instead of the servers, thousands of servers that I've written there, think of that you have some kind of a let's say computing chip or a computing platform which has an OS and which has like maybe a GPU. Maybe your computers also have a GPU. You have a CPU chip from maybe Intel or somebody, and then all our computers can get connected to the internet through some kind of a networking framework, like could be Ethernet, could be Wi-Fi. And then most of our computers come with some kind of fans which help us cool whenever the computer gets heated. And then we have electric power, in the sense that we power our laptops through the wall socket, or we have a battery there. Sometimes when we want to use it without the wall outlet power, we can directly use the power from the battery for a few hours. So these are things which actually are there in our all our laptops these days. And data centers are pretty much the scale-up version of all of this, meaning that instead of one computer, a server is typically, let's say, you can think of 10 or 15 computers put together, and then you have thousands of these. now you can imagine, like, if you have thousands of computers, how much amount of, let's say, network capability you would need. And then what now you can think of, okay, you need to probably have, if there are thousands of servers and each server has at least 10 machines, then it's like 10,000 machines. And so how many, let's say, wall outlets and how many batteries, for example, you may need. And when I say batteries, think of a desktop computer as well. Most of us, when we have a desktop, we also have a UPS. Let's say in case power goes down, we would have a UPS to help us there for a few hours, a few minutes there, if you're doing something important. And so you can imagine that there will be so many UPS systems as well. And then you can think of, if one computer that we have, our laptop, has a fan in it to cool it. Now, if I'm talking about 10,000 such machines put together, then the amount of cooling and fans that you would need to be able to keep these machines running efficiently. And finally, one thing probably which we don't have in our, let's say, day-to-day computers, maybe desktop or desktop or laptop, is something like an electric generator. And that's because we have a UPS. It supports us for maybe when our power goes out for 30 minutes. In data centers, we would have, when I say electric power, it has the AC or the power coming in from the grid. We would have UPS, and then finally we would also have generators in case, let's say, for whatever reason, the power from the grid doesn't come for a few days. Those diesel generators will be able to keep the data center running for at least a week or so. So because typically UPS can only support maybe 1 hour of power outage, but beyond that, to be able to provide services to the user, we do have diesel generators as a longer term backup solution. So that's more like a, I would say, high level picture of a data center. Essentially, it's very much similar to what we have in our day-to-day computers, except that it's a much larger scale of our collection of computers. So in the next few slides, I'll try to get into each of these domains, like what's the network, what's the server, and so forth, and try to give some more details about each of these building blocks. So overall, what you see here is you can see some maybe something like which looks like a rack in this picture. So these are actually all these are actually servers. Okay, one rack is a second rack is a third rack, and on those racks you should see something like shelves, which are like or some kind of trays. That's one tray, the third tray, and so forth. So each of these trays essentially are a machine or a computer in its own ways. It has its CPU. It will have its some kind of, let's say, RAM and some kind of storage or memory as well. Like maybe it could be like a 40 GB hard drive or something like that. And then you can see those colorful cables like blue and so forth. So those are like the network cables which will connect it to the internet. So it's very much similar to the way we would connect our computer at home or a desktop to the, let's say, the Ethernet port, for example. And so typically the type of servers so these are essentially each rack is essentially called a server. And the type of servers, if at all we want to classify them, that typically we have in this industry are broadly into three categories. One is we would call as compute. And when I say compute, it's essentially as simple as our day-to-day computer. It has fairly similar kind of features. Okay, it would have a CPU, could be from Intel or AMD. It would have some RAM. It could have a video or a graphics card or something like that. So essentially very similar to our standard day-to-day use. And so because it's day-to-day computing application oriented, so it's called compute server. There are certain servers which are called storage servers. These are, if I have to give you an example of where a storage server would get used, it could be like for maybe storing a lot of YouTube videos. Most of the videos would be there. Lots of our Google Photos, for example, would be there. So as you can see, the application that I'm talking about here are things which we just want to keep. For example, we don't need to be serving our photos that we have stored in Google Photos, every single minute. It's not like similar to a Google search. So not all YouTube videos are played at every single second. So those are things which can be just stored and accessed when needed. And so we have these dedicated storage servers. And again, the type is very similar to what we see in our day-to-day computers today. We would have a hard disk based, or we would have a SSD based, depending on the application. We would have both. Finally, I want to get into is this which we call dedicated servers. Dedicated servers, I should say, are the most recent technologies for servers, in the sense that probably I think these have started to exist maybe it's 2010 or something. So compute like regular computers, computer-based servers have been around for a while. Storage too, like SSD probably still a newer technology though. But these dedicated ones are kind of are fairly new in the market, and their footprint in a data center is increasing. And one of the prime drivers for these dedicated servers and getting more and more popular in the filled in the data centers today is because of the lot of importance of machine learning and AI. Be it computer vision applications as well, and also a little bit to do with, let's say, this online gaming is also becoming a popular and a form of entertainment, and that's also driving some of the need for servers which have powerful GPUs present. So GPUs typically would be anything like could be from NVIDIA, could be from AMD as well, and any of the standard GPUs that you see are kind of available in the dedicated GPU servers. And when I say TPUs, TPUs are actually some are custom chips which Google have designed, and it is dedicated for machine learning applications. Next slide, I'll cover more about what a TPU looks like, or a TPU server looks like. So if you remember in the last slide when we were seeing certain racks, and here too you can see racks. Now the difference here is that if you see those cables, right, those pink and blue cables, they are actually running across the racks as well. So in the past picture, we actually didn't have cables connecting one rack to the other. All those cables are just connecting every single machine there, or every single computer there to the internet. But here, all the machines are interconnected as well, directly hardwired in certain ways. So if we call the things in the last slide as a supercomputer, as a rack is sometimes called a supercomputer, essentially. So this is essentially the one that you see here. It's like collection of 8 or 10 supercomputers put together, and this is done so that, let's say, just to give you a perspective, in this picture that you see, it has 256 TPU chips as one single computer. And for example, while the one that we're seeing in the last slide, it's like every single row has one chip, maybe let's say one Intel chip, or maybe sometimes 4 Intel chips, but that's about it. So one computer there has 4 Intel chips in the last slide, while here we're talking about 256 chips put together as a single machine here. So and why such a large scale, and why such a powerful computer? Well, these are actually dedicated for specific machine learning applications. For example, sometime maybe in 2016-17, there was a news around like an AI reinforcement learning agent playing against the world champion on this game called AlphaGo, and then it was able to also beat the world's grandmaster in that field, and that was done on something like this. So that whole reinforcement learning agent was trained and was being deployed on this kind of a network of servers. The fundamental brain of this kind of a TPU server are called ML accelerator chips, and as the name suggests, it's an accelerator, meaning that it is dedicated to speed up machine learning applications. For example, if you have to run the same kind of let's say machine learning training applications for any of the Google products like Translate and Photos and so forth, on a regular compute, it takes a regular compute server, like which has Intel CPU or something like that. It would take you weeks sometimes. Like I remember certain benchmarks that were shown, which showed that a model that can be trained in this kind of TPU servers in, let's say, an hour would take 2 weeks to be trained in the same number of chips of an Intel server. And that's because these TPU servers are dedicated, and they're more efficient in specific machine learning training applications. And then now, because machine learning is just growing as an area of application and is getting integrated to products at Google, and also it's being offered as a service to Google Cloud customers as well. So meaning if you subscribe Google Cloud and you want to deploy a large machine learning model, you want to train it, and you can then, these kind of TPU servers are also made available to external customers as well. So because of, as it's getting more and more in demand, so these TPUs, they have, I think they are also like coming through generations. Like I think we are now in the 5th generation, and there are several other future generations as well as being planned to be able to accelerate machine learning applications and reduce training and inference times. Any questions so far? Shishir, is there any questions from the audience, or shall I keep going? Okay, all right, I'll keep going then. The next thing is, I think, very critical, which is network. It's important that at a high level that every single machine in a rack kind of is connected to the internet, and so that it can read the request from the users' phones or computers, and then process it and send it back to the user. And so in this picture that you see here, what I kind of have a high level diagram here. So typically a data center, which we were seeing in the first slide here, that it has machines, for example, like thousands of servers, each server having maybe 10 machines. So you can think of that maybe we can split them in two groups, two halves, and we would call them, one of them to be a cluster, the other half to be the second cluster. And what is a cluster essentially is just like we put 5,000 machines, connect them through some kind of a LAN, and that's your cluster. So this is one local area network, and this is the other local area network. And then finally there is another level of networking which kind of helps connect the two of them. And I like give some more reasons why we have two clusters, for example. And essentially, it's more to do with more to improve the reliability, in the sense that, let's say that if this data center, we, instead of having two, if we just had one cluster, and if the intercluster network, if any of the let's say the LAN cable or something fail, then we lose connectivity to all the 10,000 machines. And just to avoid that problem, what is typically done is that we would split all the machines in the data center into maybe 2 or 3 halves. So they would end up having 2 or 3 clusters. And this is so let's say if the router here fails, you still have the other set of machines available to you to communicate to and run your tasks. So this intercluster network essentially is kind of more like a LAN. And then finally, through a router at the data center level, we get all these computers are eventually connected to the internet. Most of, I don't think any of these, I have not seen any wireless kind of network being used. All of this is pretty much Ethernet based. So that's typically what, how the networking looks like inside a data center. Like you would typically have, you would divide these machines into physical machines into 2 or 3 clusters, and each cluster essentially is to be thought of as like a large collection of machines put together. And when we request a query, or we ask for, let's say, some YouTube video, that request essentially goes eventually to one particular some machine in a particular cluster. And then I will kind of eventually get towards the later part in a few slides about what's essentially the manager or the scheduler or the operating system, which kind of takes us to the right cluster for our query. In the last step, what we were looking at is within a data center, how the network is being laid out. Mainly the concept was about clusters. And on the top slide that you see, a photo that you see here, are all the various Google data centers located all over the world. And when you say a dot, it doesn't mean there's one data center. There could be 3 or 4 out there. Okay. Point to be paid attention to is that I think the last slide we were talking about network within the data center, how a data center gets connected to the internet. And now what you can see is all these data centers are connected to each other through this graph that's being laid out. And like if you see, let's say this Europe and the US, there's a cable here. Some of these cables are actually undersea cables, and you may already be aware of these things, or maybe you may have seen in the network. Like several technology companies are still putting in investments to put together networking cables even under the sea to help improve connectivity speeds. So I think this Africa and Europe connection is one of the fairly recent subsea network connectivity projects that has been completed, and I think Google and Facebook both are one of the largest investors in that particular project. And there are several ongoing subsea cabling projects as well. But yeah, what this picture should kind of at least make you think about is that essentially all data centers are kind of connected to each other through the internet. and through certain kind of cabling, and that's what enables, let's say for whatever reason, if we lose all the power in the US and we're not able to run any of these data centers, all of these go down, still people all over the world will still be able to use Google search and Google Maps, because the other data centers over there on the other half of the world will be able to entertain their requests. So that's what essentially is kind of being shown here, that you have two data centers, let's say, and it has its own set of network that we're talking about. There are the clusters, and then you would have some kind of like a local area network, which eventually goes through the router there to the internet. And then these campus level routers are kind of connected, and so overall any two data centers are connected. And if for some reason one link fails, it will easily get routed to the other link. So overall, what I think the take-home message here is that there is a lot of reliability concerns that have gone into designing this infrastructure. So and when I say reliability, that being a primary driver, and hence we have these kinds of projects being undertaken, like putting a cable under the sea, for example. All this is primarily driven from a reliability perspective, that it helps the system or the infrastructure stay alive even if something, one component of or one part of the infrastructure goes down. Next is Borg. So we talked about the servers, the types of servers, and then we talked about network. So now I think another question, and then we talked about how several data centers are connected. Then the next question is, how are like the jobs being scheduled? Like let's say we want to play a particular YouTube video, then what's the mechanism which kind of takes that particular request from the user and then takes it to the correct data center and then the correct cluster, and then finds that thing out and shows it to the user. So all this actually is being managed by something we call internally as Borg. I've linked the 2015 paper from Google on Borg. So essentially, what is Borg? If I have to say at a very high level, it is a distributed operating system. And the reason why I use the distributed is because all these computers that we are talking about across the globe now, there are, as I showed you in the previous slide, there's a picture of several locations where data centers are present. So essentially, all computers are present across the globe, and hence the computers are distributed. And Borg is essentially a resource manager for all these distributed computing platforms. And the way, maybe just to give you an example, how do I as an engineer work with or interact with Borg? It's very something like, let's say that I want to train a machine learning model. I would just go in and I would just say, let's just say that I need this many CPUs. I need probably for my task, I'm looking at this much duration, and I'm looking at maybe this much amount, or maybe let's say it's a big image processing machine learning application. So I'll just say that I probably need 40 GBs of memory, for example. And I just need to specify these high level, let's say, kind of parameters, and then Borg will kind of scan through all the list of all the resources that it has in terms of which computer should be the one is most available to entertain my requests, and then it kind of makes sure that whatever job I'm trying to schedule or run will accordingly get routed to that particular cluster and that particular machine in that cluster. So it's designed to be fully like a regular operating system, but in the context of the scale that we're talking about of computers across the globe. So that's why it's called kind of a distributed operating system, or sometimes people also call it a cluster manager, because it manages all the different clusters across the globe. So when, let's say, any of us looks for a Google search or tries to do a YouTube search and look for a particular video, then the backend of YouTube will kind of relay requests asking for giving specific details around what's the thing that you're looking for, what's the maybe bandwidth, and what's the memory for that, etc., and all of that will get routed to Borg, and then the appropriate cluster and the machine will entertain that query. It is also designed for improving the resource utilization of these computers, in the sense that we don't want, let's say, only one computer entertaining one request at a time. Computers are meant to be multitasking. And so it is designed to be enabling multitasking as well. And so, but it does keep track of things like, let's say that there's one server and then one particular machine in that server already, let's say addressing somebody's Google search or maybe email request here. And so they would keep a track of what's the percentage CPU usage and percentage memory usage for that computer. And when I say percentage CPU usage and percentage memory usage, it's exactly the same as the way, let's say, if you press Control Alt Del in our Windows computers, we see what's the memory usage and CPU usage and RAM usage, all that. So it's exactly those same things it would see and track for that computer. And so if it would know that, okay, if this computer is only 20% CPU usage, it has still room to run more things. And so it would do that. Let's say that if it sees that a computer is already at 80% CPU usage, it will probably not schedule anything any after that. So it's designed to be really looking at every single machine. Now you can imagine that one data center has 10,000 such machines, and now there are 100 data centers across the world. So which means like you have 10,000 times 100 machines, and this is an operating system for that many machines put together. So hopefully that gives you an idea on what this scheduler or this operating system, which essentially is managing all the machines across all the data centers. And as I said, it's 10,000 cross 100. That's the scale of the number of machines we are talking about here. So far, I think what we talked about is like computers. We talked about the network. We talked about the operating system. So now we are gonna talk about a little bit more about on the more physical infrastructure side, which is gonna be cooling and electrical power. So what you see on the picture on your left here, the one which is more green, is so these are essentially the back side of the servers, the racks that we're looking at. And those little holes that you see, those are essentially the small fans that any of our desktop computers would be having. So these are those fans, except that probably there are more of them. And so what this fan is doing is that, as our computers are getting hot because we're executing certain tasks in them, so it's blowing air on that, cold air onto it, and then the hot air is kind of escaping from there and is coming into this whole long, what you can call it as a corridor or an aisle. We call it an aisle technically in the field. And essentially all the racks that we have, the fans are blowing the hot air, are cool, trying to blow cool air onto the computers to cool them, and because the cold air is kind of absorbing heat from the computer chips, so the air that comes out from any of these outlets here is hot. So that's why this whole aisle is essentially called the hot aisle or hot corridor. And what happens is that you can see that there are certain pipes running here. So these pipes would be carrying cold water, okay, and fairly cold water actually, and this cold water is then supposed to be absorbing heat from this hot air here and cool that air. So these pipes would cool that hot air, and the water in turn would get heated, and then it would go into. I'll come to where it goes, but once this air essentially cools down by losing its heat to the water, then it gets recirculated through the, you'll see there are some vents down there. It will get recirculated into the data center. Now this hot water is essentially it goes through a lot of pipes and cooling equipment called heat exchangers. There's something called a cooling tower as well, and what it does is that its responsibility is essentially to cool this water. Okay, and then the tanks that you see there are essentially water storage tanks as well. So this hot water, all I'm trying to say is that is cooled through a long chain of pipes and heat exchangers and chillers put together to cool. So to give you a perspective here, you won't some of the recent developments have been that as you can see, all these data centers, they need a lot of water. For example, now that you have 10,000 computers and you want to keep them cool, you need a lot of water. Another maybe need for water is, like as I was showing in the initial few slides, that large machine learning server, TPU server we're talking about, which is essentially 256 computers put together. So you can imagine that kind of a large computer actually doesn't even have fans, like the kind of small fans we are talking about here. which each of these computers is having, it actually only works on liquid cooling, like meaning that its heat it gets heated much more than any of these, and so its cooling requirements are much higher, and so it's only liquid cooled. So overall, the message I'm trying to give here is that there's a lot of water requirement, and hence what you'll find is that a lot of data centers are located close to some water source. Could be the ocean, could be lakes, or if let's say that it's getting hard to find water source, then it would be located in some cold climate, so that the weather there is cold, and so the weather is going to help you cool down. Like so if you kind of do some geographical research on where these are located, you will find that most of them are actually located in some proximity to water source for that reason, that the data center requires a lot of water for cooling the hardware out there. All right, going ahead. Next, we will talk about electrical power. So as you can think of, these are all, we're talking about 10,000 computers in a data center, and so it really, it's almost like saying there are 10,000 wall outlets for plugging a wired cable to run every single computer out there. Now, because it's so much of power, typically wherever you want to put a data center, it almost, and most data centers are like almost if it just to the red dotted line that you see there, just to give you physical size of what that may look like, it could be like 4 or 5 football fields put together. So it's a fairly big let's say space of land where it would exist, these buildings and this whole campus will exist. Now, to power it, typically, because these data centers, as I said, are located a bit in remote places, essentially. Like it could be places where not, let's say, not a lot of development has happened, and so many times it happens that you would end up building the power grid there, because there's no existing power utility available or grid available to support that high amount of power need. So in many cases, you would end up kind of setting up your power grid when you go there to build a data center. And it's different for maybe locations like metros, like Bombay and others, or maybe London and so forth. But those are not the only locations where data center exists. They also exist in remote locations as well, and that's more common actually. And so there you typically need to, when you go to build a data center, you first also need to build a power grid. Now, in terms of, you can see pretty much like how the power gets to the data center from the towers, or the electrical towers that you see here, cables coming from the grid. It's exactly the same the way power reaches our homes today. It's pretty much your power coming from a power plant, and then you have a substation, you have transformers to step the voltage down, and then essentially it goes into your data center. Previously, I was telling that we have UPS backups, and that will support us, let's say maybe up to an hour every single computer. But if we have a power outage longer than that, we do have a whole set of generators out there power each of these computers whenever we have longer term power outages. Overall, what you should see here is that the power that we're talking about, the electrical power that's coming in from the grid there, it is helping us run all the data center infrastructure, meaning it is also responsible for running not only the computers and the servers out there, it also is used to run the cooling towers and the cooling modules and the cooling fans as well. And the reason why I bring this point here is that in our world there is a metric for energy efficiency, which we call as PUE, and PUE is essentially the ratio of the total data power consumption divided by consumption only by the servers. And what this ratio tells us is that how much, when I say total power consumption, it means power consumption by the servers plus all the cooling infrastructure divided by power consumption only by the servers. And what it tells us is that if this ratio is very higher than 1, it means that we are spending a lot of energy also to cool the computers. Because cooling the computers doesn't necessarily mean that we are doing a good job because you are kind of spending a lot of energy in cooling, and so it kind of indicates that a lot of heat is being generated. The overall system is kind of inefficient in certain ways, and so it needs to be looked at more closely to see how we can reduce PUE. So typically what you'll see is that I've given a link here as well, where you can click and go to, once you have the slides, you can click and see what the PUE, more about PUE and what the PUE looks like across several data centers of Google. There's a public facing data there. What you'll find is that PUE is very important in the sense that if you don't want to be spending electricity, which is not essentially, let's say, helping serve a user request. Okay, so because if you are spending a lot of energy in cooling, that's just kind of a waste in the sense that it's not getting, that power is not getting directed to run a particular computer, for example. So a lower PUE, and when I say lower PUE, some of the Google actually has some of the industry's lowest PUEs. And we typically Google data center PUEs are around 1.1, which means that we only consume 10% of our total of the power consumed for running computers. 10% of that is actually required to cool. And actually, if you look at industry standards, it's about 30 or 40%. I think I'm still saying it on the lower side. So meaning that I think most of Google data centers are actually 20-30% more efficient in terms of cooling than some of the industry standards. And what I think enables that is pretty much because all these things that we've talked about so far, from servers to network to cooling to electrical, all of this is actually designed in-house. So, and that's what enables everything because designed internally, and so that kind of helps us with better system integration and hence better system level efficiency performances. So with that in background, I think I want to kind of give you some perspective about what's the electrical power consumption. Now we are talking about overall Google data centers. So that's about from the 20 terawatt hour of electricity annually across probably 100 sub data centers. It's a massive number. It's actually much more higher than some power consumption of several small countries put together actually. And why this is important is that there's a commitment at Google to reach to carbon-free energy, meaning that what that whole last line here means is that any single user request, any single Google search, any single YouTube video being played, the goal is that we would like that to be running in clean energy by 2030, or essentially we're calling it as carbon-free energy. So when I say carbon-free, what it means is that it's coming from a clean source, could be solar, wind, or anything else, any renewable source, not coal or fossil fuel driven essentially. So there's a commitment towards that. So you can see what's the power consumption up there. That's already pretty large. And then today, if you look at the data centers, they're not necessarily operating on a carbon-free energy. So we are definitely depending on what's the available source in the local region where we are putting up the data center. So it could be coal based, it could be fossil fuel based, natural gas, for example, as well. So depending on the resource available that's being used. And what Google today does is that whatever amount of electricity it's using is, let's say, coming from a non-renewable source. What it would do is that it would buy the same amount of electricity from a renewable source in some other region, and it's trying to offset that. But that's different from saying that we will start using renewable energy in every single operation of ours. So that's the goal that's what Google would like to do by 2030. And that's what kind of is one of the bigger motivations for the next topic that I want to get into which is essentially carbon aware computing, meaning that we would like to be running tasks in our data centers. Will be, when I say computing, essentially executing tasks in our data centers in a more carbon aware manner. When I say carbon aware manner, meaning that we want to be more we want to be a bit more aware about what the source of the electricity is. And so if it's a cleaner source, it would mean that the carbon profile is going to be lower, if it's, or the carbon intensity as we call it. If it's coming from a unclean source, then the carbon intensity would be higher. And then we would like our data centers to be able to respond to this carbon intensity information if provided. So typically what happens is that what we notice is that in several locations where we operate, we have, let's say, clean energy maybe during maybe the day, most part of the early morning, but towards later part we start having unclean energy because, let's say, you would have solar, but because as the day progresses, the power demand for power goes up in the grid. So the utility companies or the power companies, they need to start providing energy from sources like coal or something, and so the carbon intensity kind of starts increasing then, because it's now we have a mix of unclean energy. And then again, as the day ends, towards the night, again energy could be maybe from clean sources like wind or something, depending on how's the wind situation at night in that location. But overall, what I'm trying to say is that mostly in early part of the day and later part of the day you would see some clean energy sources, but maybe in the middle of the day you would see a mix of clean and unclean. And so overall, that was the intent, to see if we can exploit this information to see how we execute tasks in our data centers. Overall, here towards the link at the bottom is towards the YouTube like a conference that we had at Google this year, and it's a long video, like a 3-4 hour video, but it has several talks in this theme of carbon-aware computing. So I think marching ahead, what I want to get to is that most of our computing tasks are flexible. Okay, when I say flexible, it means that like, for example, you want to play a YouTube video. Actually, on a data center, on our side, on a data center side, it's okay that that request gets entertained. It can get entertained in several locations essentially. Okay, so it is flexible in that sense, that where it should be running, there's some flexibility around it. Then the next thing is, there are certain kinds of requests are also flexible with regards to time, in a sense that, let's say, for certain applications, like let's say that you are trying to upload a video to YouTube, and so there is some flexibility around that, meaning that it need not be executed right, just like a Google search at the same speed. It can take some time to be executed. Similarly, let's say that if you are running a machine learning model on Google Cloud, there's some the user doesn't expect the model to be trained, let's say, instantly like a Google search. The user's expectation is that, okay, this is a model I'm training, it will take certain time to train. So there's some flexibility. There are tasks which are flexible both on space, there are tasks which are flexible both on in terms of time as well, in terms of execution time. And so any of these tasks which are flexible with regards to where we can run them, with regards to the time aspect of it, we typically call them as batch workloads. And what we want to essentially do is that we want to use our understanding of flexibility in our computing tasks to see if we can do less computing when energy is not clean, and do more computing when energy is clean. And when I say less computing, the idea is that we have a lot of these flexible tasks. So let's say for some reason we already know that this energy is going to be not clean. So what we would do is that, because these are flexible tasks, we would move them to a data center through our network where the energy is clean. So that's essentially the idea. So we would move it to a different data center, for example, depending on a task, if where the energy is clean. For example, next is, let's say that energy is not clean at this point, but we know that the energy will become more cleaner maybe 3 hours down the line, and this is a task which is okay in getting delayed by that much time. So we would do that. We would delay it by a few hours, and then it would be running on cleaner energy. So essentially, the whole idea of carbon-aware computing is to exploit flexibility in computing tasks to respond to the cleanness of the energy that's that's powering the data centers. So that's the high-level idea, and I kind of get to more specific maybe illustration here. So what you see is when you see green, it means the blue means that the wind, the yellow would be the sun, and again the blue is again wind. And what this is trying to show is that when in between the blue and the yellow, the amount of computing running is low because the electricity is not clean. But whenever you have wind or sun, the amount of computing you're running is much higher than your traditional computing data centers. So that's what we're trying to exploit. This full gray picture is our traditional data center, where we are not aware about the carbon part of our power. But now because we are aware, so we will be running more when sun and wind is present. We will be running less when we don't have sun and wind. And so that's the long term, I would say, direction that we are trying to take. And I should say that we have already begun implementing this, and with in future we're just going to get more aggressive actually with something like this. Next I want to get to is like I think there are some certain more applications of probably how job flexibility exists across various companies as well. So this is the kind of flexible jobs I was talking about. It's present not just within, let's say, Google's the type of jobs Google runs, but also other companies have their notion of flexible jobs, both in time and space, and they should also be be doing something along these lines. That was actually one of the outcomes in that conference. I would say it was a multi-industry conference where they talked about how can other companies to put together carbon awareness in their data centers. So fundamentally, what we have is essentially what we call as carbon intelligent platform here, which what it would do is that, as I was telling you previously, there is this scheduler called Borg, which connects and manages the tasks that we are running on all these data centers. So what it would do is that this carbon intelligent load management platform, it would guide this operating system called Borg and to see how it should be, how much job it should be scheduling in one data center versus the other, depending on the carbon profile. So, for example, is that the carbon intensity. So let me first talk about this black line here. So this black line is, let's say, when we were not having any carbon awareness, this is how our data centers were running maybe 2 years back. So in this occasion, what would happen is that we are during the day, middle of the day, a lot of let's say energy from solar plus coal as well, and that's the energy profile. Okay, it's the power profile. And what we would do is we would be running all our tasks in this time of the day as is. So meaning that we are running a lot of tasks also in the unclean time. Now, when we looked at the carbon profile, the green line is the carbon profile of that power grid out there, and we found that okay, it looks there's a lot of carbon intensity during the middle of the day. And so what this carbon intelligent load management platform does is that it would take away all the flexible tasks and it would send it to another data center down here, where you can see the carbon profile is actually lower during the day. And so eventually what you can see is that the power profile now goes down because you have moved out a lot of the computing tasks from the data center. So you're actually consuming much less power, which in turn means that you are actually consuming much less unclean power when power was coming from unclean sources. And then once power becomes cleaner, you can start running it at the usual intensity level of load. So and why is this possible is because it's like a simple, like a time zone gap essentially. Like when it's daytime in the US, it's night in India. So it's and when it's night or the daytime in India, then it's night here. So it's easier to kind of balance this carbon, the different carbon intensities across different locations and exploit that to be running your operations in a much more cleaner fashion. So overall, what this carbon intelligent load management does is that it adds this carbon awareness to the operating system called Borg. So you're just checking in how good are you with time? Okay, all right. Yeah, I'll try to wrap it up in maybe by 10 minutes extra. So if, maybe I'll go quickly to probably, okay, this slide. So I'm just continuing the same thought here, which was we were talking about bringing in carbon awareness and then shifting the load during times of the day when energy is not very clean to a different location where or to different time of the day where energy is cleaner. So overall, what does the operating system or the scheduler sees or Borg sees on its end? So typically what it would see is this thing what we call as default cluster capacity, meaning that it will see the resources all the entire set of machines in that cluster, or the entire set of servers in that cluster is having. Now, what this carbon intelligent load management platform, what it does is that instead of it tries to override that. What it says is that your capacity that exists is actually this red line, which means that it's saying that, especially I think this part is interesting, where before we started doing this carbon intelligent load management, Borg would see this default cluster capacity. Now, with more carbon intelligent, as we have implemented carbon intelligent load management, so today, during the time of the day when energy is not very clean, when your carbon intensity is high, what it would see is this, meaning that according to Borg now, it is only seeing this is the amount of resource that's available to schedule jobs. So that's fundamental idea that we have implemented. That what we do is that we have an optimization framework, which tells us that based on the carbon intensity profile for the next day, that what should be the resource that or the capacity that Borg should be seeing for scheduling jobs. Because the way Borg works is that it just needs to look at how much CPU is available, how much RAM is available, and how much less storage is available, so forth. Okay, and typically before we're not doing any of that, it would just read it directly from the machines about how much CPU is available and how much RAM is available and so forth. Now what we are doing is that we are based on the carbon profile. We are telling Borg that okay, we have data available, forecasting available for tomorrow's carbon profile, and based on that, during this time of the day, your resource availability is only this much. And then when energy becomes cleaner, we say that your resource availability is higher. Okay, so when we do this, what happens is that that's the total load. That was the original total load. Okay, and there is an inflexible component, meaning the hard or the rigid component, which we cannot let's say move to another location or another time of the day. But there is also this large flexible component. The difference between this two is essentially the flexible load. And what will happen is that all of this load will get directed to some other time of the day where we are having more cleaner energy. So essentially, at this point, Borg actually doesn't see resources to run flexible jobs. It only sees resources to run flexible jobs when energy is cleaner. And so that's why it will wait and schedule those jobs only when energy is cleaner in that location. So that's, I would say, a high level idea of how this whole thing is designed. Getting into the more specifics of what are the things that are needed to build this platform. The first thing is to have what we call as carbon intensity forecasts, and that's available on a day ahead basis. So there's a startup that's partnering with Google on this, and they provide carbon intensity forecasts for all the locations at which Google has data centers. Next thing is to be able to know our load profile, in the sense that we would like to know, because if we're trying to do a planning for the next day. So we need to and when I say planning for the next day, meaning we're trying to inform Borg, the operating system, about the resource capacity available for the next day. And so we need to know how much jobs we plan to be running. So it's kind of it may sound a bit strange in the sense that you're trying to do a day ahead optimization essentially, and for that we need to be able to predict what's the flexible load that we expect for the next day, and also what's the inflexible load for the next day, because data centers will have both of this component. The flexible component is something we cannot touch, and we cannot move to a different data center. We cannot delay it as well. So we would need to have forecasts for both of these, and that's where I would say time series forecasting or some kind of forecasting from ML and AI are being used. And it turns out that these things are very well. It's not very hard to kind of predict or forecast load profiles. Things are very fairly, I would say, predictable, and have nice patterns to be able to design a forecasting algorithm to predict them. Finally, what we need is a map which will take all these jobs when you run in a data center to convert this load profile into a power profile. And the reason for doing that is that we are essentially interested in two aspects. One is that we want to minimize our carbon footprint, And the other is that we also want to minimize the peak power that we consume in a data center, so that overall we are trying to reduce our energy consumption as well. So that's what this optimizer has. It uses the carbon footprint calculation, and the way it's done is that we have our load forecast for the next day, for both the flexible and the inflexible usage, and then we convert that into a forecast for power. And once you have a power forecast available, if you multiply that with the carbon intensity forecast, then it kind of gives you the carbon footprint for the next day. Okay. Now, then from your power forecast, you also have the peak power made available to you as a forecast for the next day. And your objective is to how do you actuate the flexible load? So how do you actuate the flexible usage for the next day, so that the weighted combination of the carbon footprint for the next day and the peak power for the next day is minimized. And then when I say, the reason it's called global carbon intelligent computing system optimizer is because this objective is to meet the minimum. This minimization objective is across all the 100 data centers, let's say, we have. So we would solve this optimization problem a day ahead. We would calculate what I'm calling as, based on the output of this optimization, we are calling it as virtual capacity curves. But what that essentially means is that what's the resources or the capacity for each cluster Borg should be seeing depending on the carbon intensity of that location for next day. And so what would the output essentially looks like is that during hours of the day when energy is not clean, Borg would see much less resource in that cluster, so it won't be able to schedule a whole lot of flexible jobs there. It will only be doing the inflexible jobs. An inflexible jobs example is like a Google search for somebody. So that would be one example of an inflexible job. But there are several flexible jobs, and those won't be running in times of the day when energy is not clean. So that's the output of this high level, I would say, optimization problem here. Finally, this optimization does have certain constraints which are more to do with certain kinds of resource constraints. There are certain performance constraints as well, which we put. I'm not going to get into the details of those. You can the paper kind of talks about all of that. I just wanted to give a more high level systemic diagram here about what the system essentially looks like, or it entails to build a carbon aware sensitive computing scheduler. Finally, I think what is maybe making this thing useful or are like the following things, which is I think mentioned here. So what we have a good hold on is we understand our load profile very well. So that's why and as I said, it's very predictable, and it's very even simple algorithms can be used to predict the flexible and the inflexible load profile for the next day. And another big lever here is that we do have this carbon intensity available in most of the locations. So that's definitely a big enabler in all this. And these things were not available. Mainly this carbon intensity, for example, it was not available, let's say, like 5 years back, for example. So there was no such tool which would provide you a carbon intensity of every single location where you are generating electricity. And just to have a company which does that and provide that data is driving, let's say, this Borg to become more carbon sensitive now. Finally, just to give you an idea, because that we are solving this optimization for hundreds of data centers, so at a single go. So the thing is that this optimization needs to be scalable. Okay, so meaning that we should be able to solve it in certain, with some guaranteed time duration, and what it entails is that's what it required us to be building models, or for example, the optimization problem should not be a non-convex one, if some of you understand that word, because if you are solving a convex problem, then you are at least guaranteed to converge in reasonable time, and you will be able to pass on that information to Borg within the time it expects the results. Otherwise, if it becomes a non-scalable problem and it doesn't finish in time, then essentially it's not helping us become carbon aware in several ways. So because of these kinds of performance and scalability, let's say, requirements that we have for it to work for all the data centers across the globe, the optimization problem is actually a linear program. And there are several, let's say, we initially began with several complex power models and load profiles forecasting models as well. Like when I say complex, it's more sophisticated to then something like it's more sophisticated than simple regressions or anything. It's more to do with, let's say, could be a deep neural net or something like that. But eventually, when we wanted to work for all the data centers across the world, now our forecasting algorithms are more traditional time series forecasting methods. Our and the people will talk about those kinds of methods. It's more to, just to give you names. It's like ARMA models, ARMA models for time series forecasting. Then for the power models, for to convert a load forecast into a power forecast, those are piecewise linear regression. So and what we doing these simplifications helped us get to an optimization problem which can be solved within a reasonable time, so that it can be used by the operating system. So otherwise, it was taking much longer, and we were not able to give guarantees that the optimized capacity curves will be available for the operating system to pick. Finally, I think this is just trying to highlight the two aspects that we're trying to minimize. One is the carbon footprint. The other is the peak power that we consume for a data center each day. And we solve this optimization problem day ahead, meaning for the next day, every single day, for every single data center that Google has today. So it's kind of being implemented fleet-wide. Now, what I want to show is finally, I think, is maybe this one real data picture. So far, whatever and I've been presenting is mostly like I would say an animation or something like that. So overall, what you see is I think this is the one that you. So this is for one particular cluster, okay, and the black line that you see is the carbon intensity profile. You see is that the output of the optimization is the global optimization that we solve is essentially this red line called virtual capacity curve, and what it does is that it tells the cluster that okay, the amount of resources available during the time of the day when the carbon intensity is high is lower than usual. Okay, so you see how it drops, and so the blue line, the load in the cluster also drops, and now you can see that as the load in the cluster drops, you can see its power consumption is also dropping, and so you are consuming much less power in the times of the day when energy is not very clean, and hence it's helping reduce the carbon footprint of running the data center. Now, what happened to those tasks which otherwise, let's say if we hadn't put this VCC here, then there would be other tasks running here. So what happened to those tasks? Well, either those went to some other data center or those got delayed depending on the nature of the task, and the optimizer takes into account that aspect. And so in the previous slide, what I was showing was for a cluster. And as I was telling you that a data center is typically a collection of 2 or 3 clusters. So, we have so this is more like at a data center level, how this thing looks like. So your green line here is the carbon intensity profile. And you can see that there is a time of the day when it's higher than, and there are times of the day when it is lower. Now, if you were not doing this carbon intelligent load management approach, then the blue line is essentially the way the load was running in that particular data center. Okay, so you can see that our power consumption and hence carbon footprint is much higher. Now, once we implemented our carbon intelligent load management at Google, then you can see that during this time of the day when the carbon intensity was higher, the load in the data center and the power went down, which kind of improved or lowered the carbon footprint of the data center. And then it caught up again when energy started becoming cleaner. So that's fundamentally what's kind of happening at a data center level as well. So it happens at the cluster level, and then if you aggregate at the cluster level what's happening at the cluster level, then you get to see what's happening at the data center level. So I think this is probably also my last slide here. So finally, I think what is the future here is that we want to. So today we do a lot of shifting in time, meaning that we delay tasks. We are not doing a lot of shifting across locations, meaning let's say India to US transfer of a task. and not all. I mean, we still do a little bit, but not a whole lot. We do more of shifting in time. So what we want to eventually get to is to be also be doing a lot of shifting across locations. And presently, the limiting factor to that is that our networks are not that let's say fast enough to be able to shift tasks from one location to the other. So not all kind of tasks we are able to shift. And so there's a lot of work now going on to be able to put together the network infrastructure to enable this shift of tasks from one location to another based on the carbon profile. Let's say if carbon is high, carbon intensity is higher in the US, it's lower in India at that time. At the same time, we just move it to India, for example. So that's something that's very actively being worked on right now. It's a very active project in terms of how do we shift load across locations and then make it sensitive to the carbon information and exploit that. Finally, as data centers are a massive power consumer, there's also a lot of activity going on to integrate it to the grid. In the sense that how could data centers support the local grid in terms of providing infrastructure in critical times. Like as I said, if there is data centers have lots of generators, lots of power sources to power. I mean, we looked at certain numbers, like total power consumption of all Google data centers is almost equivalent to several small countries put together. So can data centers help the local community by providing the power in these regions, and how do we integrate data centers with the local community's power requirements? So that's another problem that we are very interested in is to, because we have already built this massive infrastructure now. It's more trying to see how we can share this infrastructure to run and help the local community in terms of their power requirements. So that's another way to reduce the carbon footprint, in the sense that it's like if only one person is using all this energy versus that same energy, if it can be distributed to the others, then your individual ownership of that carbon footprint becomes lower. So that's the idea there, that how do we participate more with local communities and help meet their power requirements. And this whole carbon intelligent load management that I presented so far, we want to extend it to more flexible loads, and also to enable better integration and load management when we are part of the community outside the data center as well. I think that should be all from me. Thanks for listening. I would be happy to take some questions here. And I apologize for, I think, going 10-15 minutes over time.
No, not at all. Um,
Yes, you can proceed.
Yes,
I think
yes.
Saurabh, it was a excellent talk. You briefly talk about how Google Data Center works, and all those things are actually helpful for who is listening to this talk. So may I request you to turn on your video so that we can, if it is possible. So
You think turn off or turn on?
turn on. Yeah.
Are you able to see me?
1 second. So and Vigan will actually there are some questions in the YouTube live chat. So he will actually he will give the answer, question, and you can just answer that.
Okay.
1 second. I can watch your video. Yes. Okay, fine. Vigan, you can go ahead.
Yes. Okay. So thank you, sir. It was a really insightful session. We do have a few questions on YouTube, so I'll ask them. The first one is from Hira Shankar Datta. He asks, could you please elaborate on the significance of the border router? Are the border routers only connected to each other via inter-cluster network?
So are they able to see my screen, or I just answer it verbally again? I can if I move to the slide, will they be able to see the screen?
Yeah, it's the presenting. Actually.
Okay, awesome. Okay, then maybe I'll just also go back to the slide based on the question. So I think the question is related to this particular slide, and Yes. I think the as the question said it's only through the border router. That's how the clusters get connected. That is correct, and I can confirm that. Yeah.
Okay, so the second question is from Azhar Laskar, and he asks, is it right to assume that in order to achieve reliability, the data, say a video, has multiple copies stored across different data centers? In that case, is there a rule as to how many copies is enough?
Yes, the first thing is correct that to ensure reliability of operations, there are multiple copies that exist, and I specifically do not have, let's say, the numbers on how many copies, but I can give you the idea how that will be calculated though. So typically what is done is that we have a lot of people actually who are experts in, I should say, um, statistical reliability. And what they would do is that they would run a lot of probabilistic failure simulations. And what the things that decide how many copies and all is that they would run this probabilistic failure simulation, and we have specific requirements that our probability of failure should be less than, let's say, 0.0001, like 5 zeros and 1. And so in that simulation, then they would feed in this kind of inputs of the number of copies, and whatever the number of copies leads to a probability of failure less than that particular threshold will be the one that would go in. And so this is all algorithmic in the sense that these are designed, and the system kind of decides on its own in a way. But what I'm just trying to give you some perspective on what kind of a reliability and probabilistic simulation is essentially deciding the number of copies here. It's primarily driven by the probability of failure threshold that we would set.
Okay, the next question is from Sisir Kareta. When we watch a video on YouTube, how much greenhouse gas emissions happens?
Very good question. So I usually actually don't have specific data on one individual task. My vision has always been on focus has always been on an aggregated of everything running together at the data center. But I can maybe Shishir, so there's one paper I think I remember reading from actually MIT, which talks about CO2 emissions of various machine learning tasks, and some of which are also being used within YouTube as well. So YouTube recommendations, for example, also use some of those kinds of models, and it kind of compares the carbon intensities or the carbon emissions of BERT and other standard machine learning models as well. So maybe I'll try to find a paper and share it with you. And if I find some more data around how much does it was the CO2 emission for a single YouTube task, I'll try to get that to you.
Okay, then next question is again from Azhar Laskar. Is water cooling the only viable option today, given the magnitude of the problem? Is it the environment concern or cost concern that keeps Google from using the other cooling technique?
Yes, so that's a good question. So interestingly, there are some, I can tell you what's probably the technology that are being investigated right now actually. So some of the things that are being investigated is to put a data center inside the ocean to see if that's a viable solution from a cooling perspective. And I think Microsoft has already done that. You will be able to, if you just Google it up, you'll be able to find some Microsoft data center, Microsoft kind of exploring, and they've already done one pilot of a data center that exists under the ocean. So that is one option, I think, technology that is being widely investigated right now across several companies now. Now, one of the main, I think, driver here is the cost. So I think what has happened is that there are a lot of cooling technologies available which are better and efficient than some of the ones probably we are using today. But what happens is that when you try to apply those technologies at a scale of, let's say, the data center, which I'm talking about is 10,000 computers and so forth, that's when those things don't scale well in terms of cost. So yes, I think there are technologies which maybe are comparable in price when we look at a maybe smaller scale. But what has been challenging is that the way the kind of scaling benefit you expect when you're building for a data center for 10,000 machines, for example, that scaling that you get with water and has not yet been available from a business perspective. And I think that's one of the reason for resistance on the change there.
Okay, and we have another question from Shishi sir. How does Google use power optimization in grid? Can you give a brief overview? It will be helpful for the students who are working on grid power optimization.
Correct. So okay, just to give you one example of how Google can participate in the grid. If you maybe look up for one of the past, maybe this year's news items in January or February, what you would see is that there was so Texas is one area in the US. Its climate actually is fairly similar to actually India. Okay, in most ways, like it's like nice and warm during the winters. Actually, I mean, I don't think winters in India are very cold. Especially, I'm talking about maybe let's say like the like Guwahati or maybe Bombay or these kind of places. Yeah, definitely. If you go very north, it is cold out there. But so Texas typically is like maybe similar to Bombay kind of a climate, and so they never expect any kind of snow in the winters, for example. So what happened this year in January was that Texas received snow, and because of that, because their power infrastructure is not designed to be for a winter weather, it's designed for something more summer kind of a weather and more humid kind of a weather, and because of which there was massive failure of power grid. And this is like a big episode actually, like almost for several weeks people didn't have power. It was snow, heaters were not working, so you can imagine what's the kind of situation that we're talking about. And then we have data centers running there. And as I had told initially, that data centers kind of typically set up their own power grid and all that because they end up being in remote locations and so forth. So several data centers, not just Google, but Microsoft and other companies also, what they were able to do was that they were able to connect their data center power grid to the main power grid. And they were also able to reduce their power consumption by removing or eliminating all the flexible load running in those data centers. And just to give you certain numbers, it's almost like saying like one of the Google data centers, it dropped about 20 megawatt of power. Okay, and similarly, you'll see reports from Microsoft as well doing something similar, and others also doing something similar in that area. So that's one example. Like right, for example, it was a catastrophic event. Many people didn't have power. The main grid had failed, and then there were these data centers who were having their power grid, and they were able to reduce their load and take on the load of the people around there, so that they can get some power. So hopefully that kind of answers that question a little bit. So that's maybe one practical example where how data centers interacted with the grid and provided power when it was needed. That's more like a catastrophic or an emergency scenario. The other scenario I want to talk about is more like a day-to-day usage. So what the day-to-day usage is more like, let's say we are drawing power from the same grid. We're talking about a data center in Bombay. In Bombay, we don't have our own power grid, for example. So we're drawing from the power from the same grid as the people living there. And so, for example, let's say that there is a power shortage because everybody has it's a very hot day. Everybody wants to use their ACs and everything. And so now what the data center there can do is now that if we can get an input from the grid that okay, it's a very hot day, everybody's going to turn on their AC. So data center, if you can lower your power consumption today evening so that others can run whatever they want for their comfort, that would be very helpful. And so what the data center can do is that it could take that whole flexible jobs component from there. You can just move it to some other location or delay it and help meet that peak power requirement. Otherwise, what will happen is if the data center doesn't respond to it and people turn on their ACs, there will be massive peak power spike, and overall everybody will lose power. So that way, it can interact with the grid to help sustaining the grid for long and avoid all these kind of blackout situations.
Okay, and we have the one more question on YouTube. This is from Saurav Talukdar. He's asking what steps are taken to keep the areas cool, as a lot of heat is dissipated around the infrastructures like data centers.
Yes. So coming first, I think is locations, how they're selected. So of late, there is a lot of focus on trying to see if we are able to select locations which are in cooler climates, and or almost like saying next to a lake or something, which again the lake itself would be cool, and so that heat doesn't impact that. Now, forward looking though, the plan is that because we are also talking about these cooler places, so meaning that there when it gets cold, people actually need heating, and so there's some efforts going on to seeing how can we direct this heat that we are generating here towards heating solutions for people's homes in that community. So that's one aspect that's being impacted. I think this or investigated. The technology, I mean, at a high level, it's called district heating. Is the concept here that's, and you can look up more about what's district heating, and how maybe data centers are trying to see if they can help with district heating. That's one of the options here for that's being looked at to see how we can utilize that heat that's being generated. Apart from that, today at least what's being done is that because these locations are anyways in colder, many of these locations are in colder locations, places. So at least most of the waste heat is recovered for heating the office buildings so data center locations will also have office buildings for the staff who would be responsible for running it and maintaining this infrastructure day in and day out. So it's like a 24/7 running office. There always somebody who's working there. So at least today we are using a lot of our recovered heat for keeping those buildings warm. So the office buildings, I mean. So we're trying to see if that idea can be extended to locations which are where people are living, but it's a bit away from our data centers. So, but yeah, that's the challenge that's being that is being tried to be tackled now.
Okay, thank you, sir. That is, I think that those are all the questions from YouTube. I wanted to ask, sir, about an overview about how was your career like from being a machine learning engineer to going to like Google, as you said, that is a predominantly technology company and working in Google as a control system engineer in data center. So how was that journey, and how did you approach like Google as opposed to other maybe conventional maybe companies for mechanical engineering?
Yeah. So so my background was primarily mechanical engineering, and I should say, I think fundamentally my interest, if I have to say, it has always been around some kind of, I should say, maybe applied math, which when I say applied, in the sense that mathematics or stats which is mostly geared towards some kind of a physical system, could be these data centers we're talking about, or it could be maybe cars or robots or things like that. So that was what's what my interest academically was, and also continues to be. And what happened was that in terms of my PhD, I did focus in applying optimizations and some of these things in the context of smart power grids. So that was, I would say, the background which kind of helped me kind of get set up in terms of, let's say, being somebody who is able to visualize or create concepts that can be applied for optimizing power consumption, be a grid, mostly in the grid setting. That was my academic background. How should grids look at optimizing their energy consumptions? And if you look at data center, there are several, I should say, commonalities around between these two, between the data center and the way we have our grids set up today. So that was, I think, the bridge there. But overall, I think one of the points was that well, Google versus something else. So I think that the one thing about Google, which I think I do like, is about things are very dynamic, in the sense that we are kind of the company is kind of very looking at current trends. It's always forward looking. It tries to set goals very at a much faster pace, and what should the goals be. So yeah. So I think from that perspective, it doesn't like to stay in one particular. Let's say we did one particular product and we did one technology, and let's say feel comfortable and happy about it, but doesn't like to stay complacent about it in certain ways. So it's always willing to try to push the boundary a bit more. So that's one aspect of the company, which definitely is something I should say I've liked it quite a bit. And I don't know of many places which always tries to push once you get through something and tries to push it further. That's almost like the thing that I've seen common across several projects here.
Thank you so much, sir. I think we don't have any more questions on YouTube. So, CC sir, should we conclude?
Yes, yes. Thank you very much, Saurav.
Yeah,
So
no worries.
yes,
It's a pleasure
we
to
can. I think we
present to
can
the
stop.
audience.
Yes. Yeah.
Yes, sir. Yeah, once again, thank you, Dr. Saurav Talukdar, for that engaging session for all of us. I think if even though if maybe some of us might have had a very overview or a vague idea about these topics, but we got a very concrete, more concrete picture from you. So that will definitely be helpful. Just the last thing, sir, if maybe anyone watching here or on YouTube wants to contact you regarding questions or doubts, will they be able to reach you? And if so, then where? How?
Yes, so I think my LinkedIn would be I think would be the best option to reach out to me through LinkedIn. I think, and they can and then you can set up time or we can continue chatting on LinkedIn as well. Yeah.
Thank you, sir. So with that, I think we can conclude today's session. Thank you thank you, sir, and thank you all those who are watching. Thank you.
Yeah. Thanks,
Thank you.
I for
Thank you.
hosting me. All right. Bye bye.
Bye.